Yeah. So I would be presenting to you about the function delivery network. So does everyone has seen the slides of function as a service, serverless computing? I think no. So I will give you a brief introduction on the serverless computing. So before going into the details of function delivery network. So this function delivery network is what we are doing at the chair. So this is to give you a bit of a like idea of what research path we are doing at the chair. So what is serverless computing? So as you have already seen through the lectures of this class, so first we introduced the bare metal or the traditional IT, which was like the unit of the scales were the physical servers, and these deployment would take hours and live for years. But with the introduction of the function with the introduction of the virtualization, so there was the infrastructure as a service, so which you have already seen as part of the first few slides of this lecture. And then you can deploy your application on the virtual machines, which usually live for a week and have a deployment time in minutes. Now with the containerization, so with the OS level virtualization, so there was a cloud model as a platform as a service, which you already know. And you can deploy your application within the containers, and they live for minutes, hours, depending on how long your application is. And the deployment time for them is around seconds. Then all of these are server based. So what do I mean by server based? Like the user has to specify certain configuration parameter to deploy or configure the servers over here, like the auto scaling parameters, like the minimum and the maximum amount of the scaling of the virtual machines, all those parts within these all three deployment models. But around 2014, so I think around Amazon introduced the serverless computing. So by serverless computing means the user, as you as a user or application developer, does not have to worry about the backend infrastructure. So that's that's hidden from the user. So all the configuration parameters or whatever the things are required for the backend is hidden from the user, and that's what is called as a serverless computing. Within the serverless computing, one of the major, like the model is the function as a service. So this is where you deploy your application as a functions. So the functions are, let's say, like you have an application in Node.js, and you have the get API, post API, and these get are doing like querying the database, getting some data, and that particular part is like a part of the application becomes a function over here, and they get deployed in milliseconds or seconds and live for seconds. So because their duration for the running duration is less than, depending on which platform you are using, so it's less than 5 minutes. And this is called as a serverless. So there are other models as well, like backend as a service or a container as a service. I think in the Professor Gent slide you would see about the backend as a service as well. Another thing to note over here that the focus on this function as a service or the serverless computing is majorly on the application side. So all the other things related to the infrastructure are hidden. And also you can see the amount of the virtualization stack in this serverless computing is quite big. So there can be a certain amount of an overhead if you are using this serverless framework or the platforms. So as part of the serverless computing, so you have to build your application. So you have to build your application in a way that you can deploy on it. So one of the so the first application as part of the exercise which you have developed was in a kind of a monolithic way, where you put together everything in a single container or a single virtual machine, and the user interface and the backend were all clubbed together. But in the third exercise, you distributed the work into individual microservices, which you can see over here. And over here in the function as a service, the distribution of individual microservices is further broken down to individual functions. So as you can see, the catalog microservice could have multiple functions. So they can be divided into two functions over here. Similarly, the payment microservice and the order microservice. So this is usually how the fast-based application look like. So the user sends a request to the load balancer, Load balancer sends it to the user interface, which you have for the application, and this then interacts with the backend API gateway, and then it forwards it to the different functions which are doing some different purposes. So to give you an example of what function looks like, so here is one example. So as you can see, it's in Python. So you have a function name, so like a define handle, so which is handling the request, and it takes a certain parameter. The parameter is the file size over here. The file size is like how much you wanna do the compression part. And then first what I do is I write some random numbers, random bytes into that particular file. So I calculate that latency, how much time it takes for writing that particular amount of data based on the user specified the file size. And then the next thing I am doing is a gzip compression. So like the Linux command for doing a compression over here. So I'm compressing that file. So it's like how much time it took for firstly writing, and second is for the compression. And then you can see I'm just returning that information. So this is just a very simple function which you can write in the serverless. So here you can also have other kind of APIs like querying into a database, doing certain things, and then sending a response back. So, but the other parts you don't have to worry about in the serverless computing. So now the next question is how this is working in the backend. So like function as a service. So you have seen it from the front end, like you deploy the function, but how the infrastructure or the serverless platforms are doing it for you. So basically for invocation, so by invocation I mean like the user request. So this could be user request or other events. By other events I mean like you have let's say you have an IoT device, and that IoT device is publishing a message to the MQTT broker, and that message becomes like an event. Whenever there is a message published, so something has to be triggered. So it's like an event-based mechanism for the whole serverless computing. And these events are taken as an input to a fast platform. Fast platform or a serverless platform is like a AWS Lambda. So we'll see more about them. So what that platform does is it checks if I have a free instance. So by free instance, it means like, let's say if my platform is running the functions within the container, so then this free instances, it will check if I have a free container. Or if it is a virtual machine, it will check if I have a free virtual machine to run the function. If not, then it will do a start of the instance. That instance could be a container or a virtual machine. So we'll see why I have written over here a cold start in the next slide. So once it's started, so now my container is running where, or the virtual machine is running where now I can run my function. So then the platform would execute the handler method, which you saw in the previous slide, the function handler method. And this instance now consists of few stack. One part of the stack is the execution environment. By execution environment is like the container or a virtual machine. Then the runtime. So like in the last slide you saw the function was written in the Python. So this runtime would be specifying all the libraries required by the function to run, like the Python dependencies and everything. And then the main function, which is a function handler method, which we saw in the last slide. So then once it is run, then the response is sent back to the user. So now you can see, so if the instance is like it has to go through this particular path, like every time if I send a request, it has to restart the new instance time and again, then it would be quite an overhead. So then usually if I have enough number of resources, I can directly send the request from here to here so that I don't have to go through this path. And there are a lot of research going on how you can reduce this thing. So I'll tell you more detail about what a fast platform or a serverless platform do over here. It first downloads the code required for the application to run, start of a new instance, so it's like a starting of a container or a virtual machine, then bootstrap the runtime, like loading the dependencies required by your application or the function to run, and then execute the handler method. So as part of the cold start, which goes through this path, so it has to do all these things over here, like downloading the code, bootstrapping the runtime, starting of the instance. If it is a bomb, which is directly over here, so I know my execution environment and the runtime is ready, so I can just execute the function handler method and send back the response to the user. So this is called as a warm start. And on the left side, this part, which is the code download and the start of the instance, is the responsibility of the fast platform, like the AWS Lambda or some other ones. And on the right side, it's your responsibility to reduce as much time as you can do for this particular bootstrapping the runtime and the function handler execution. So like reducing the amount of dependencies within the function and reducing the amount of code within the function. So you can reduce this optimization over here. So to give you an example of different fast platforms or serverless compute platforms. So in the public cloud, there are different ones: AWS Lambda, Google Cloud Function, Azure Functions, or IBM Cloud Functions. Does anyone have of you used any of these? Maybe AWS Lambda. Which AWS Lambda?
Both Lambda and Google Cloud Function.
Okay. Do you have any preference, AWS Lambda or Google Cloud Functions? No.
Same both.
Yeah. Okay. Anyone else? And then there are open source ones. So one of them is the Apache OpenWhisk, other is OpenFast, and the Knative, which is quite popular these days. Any one of you have any of these ones? None? So if you have used the IBM Cloud Function, they use the Apache OpenWhisk within their commercial version over here. So it's based on the Apache OpenWhisk. And the Google Cloud Function is based on the Knative. Yeah, so these are different cloud serverless compute platforms or the fast platform available. There are many more in the open source, and there are others also in the cloud offerings. So another thing which I just give you a brief idea, this edge cloud continuum, because it was on the title of the slide. So what is this edge cloud continuum? So it is like a cloud layer. You have your virtual machine or the servers in the cloud layer. Then you have an edge layer. By edge layer, I mean like the devices closer to the user. So let's say I have an IoT device and there is an edge server which is much closer to me. Then I have to go to the particular data center, let's say in Amsterdam or somewhere, which is in the cloud layer. And the end devices could be like your mobile devices. So let's say you have a mobile device capturing a picture, goes to a certain edge layer within the Munich. And from Munich, it is also sending it to the cloud layer for doing some extra pre-processing or post-processing, depending on how the application is written. So this combination of all, so I think, so these two, cloud and edge, makes this edge cloud continuum. So it's like a free-flowing, seamless integration of the edge cloud continuum. So does anyone have any questions here? So before I go into the other aspects, which is now more towards the function delivery network. Okay, so now you saw briefly about the different platforms. So there exists heterogeneity in the serverless deployment. So like if you deploy a function on the different platforms, so there are different heterogeneous parts. One of them is the hardware configuration based. So by hardware configuration, I mean like, so you can deploy your function on any of the platform by specifying certain memory. So the memory is the only parameter required from you to deploy the function. And this is how it varies. So if you specify, let's say around 256 MB of a memory to a function, so then your response time would be around 1.5 seconds for a certain application. And if you increase the memory, you would have a 0.5 response time. Can anyone tell me why by increasing the memory, I'm getting a less response time? So the application is not a memory intensive. So still I'm getting a less response time with the increase in the memory. You have used it, maybe someone else. No? So yeah.
Well, in Lambda we can specify only memory when we specify hardware configuration. So when we increase the amount of memory, Lambda automatically also increases the number of CPUs allocated for this Lambda.
Yeah, so he's right. So in the most of the cloud serverless platforms, so there is a mapping between the memory and the compute. So how much you specify the memory, there is a mapping specified. Like if I specify 1 GB over here, then I would get like 2 virtual CPUs. If I specify 256, I would get 1 virtual CPUs. So that's why, so whenever I am increasing the memory, so there is an increase in the compute power for the application or the function to run. That's why you can see it's reducing down over here. So another thing, now it becomes constant actually after this particular time. So another thing to note. So this is because the application is not multi-threaded. So if after this particular point of time, you keep on increasing the number of virtual CPUs, so the application is not using those. So it will only use the one virtual CPU. So that's why the response time over here, it becomes constant, and it doesn't matter even if you increase the amount of compute power over there. So this is just to give you an example that there exists a hardware configuration. So if I deploy my function with 512 or 2048, so I would get a different response time depending on what hardware configuration parameter I'm specifying. The next is the location based. So by location, I mean like you can deploy the function in different regions. So like in the US East, EU, or Asia Pacific South. And based on that, you would get a different response time. And here one can also include like an edge location, so like closer to the user. So depending on where my function is running, so I would have a reduced like a high response time for an application or a function. The lastly is the platform based. So you saw earlier there are multiple platforms, and each platform has their own variation of reducing the cold start or optimizing the different parameters. So that's why you can see within different parameters, you can have a different response time. So like if I am running an application for 120 with 128 MB of memory, I have a different response time over here. So you can see IBM Cloud Function is behaving the worst. So then around GCF and the AWS Lambda are almost similar. And then there is an OpenWhisk, which is deployed on the self-hosted platform. So you can see different variations within different platforms you can figure out. And these vary with the application also. So like this application was doing nothing. So if you have a compute intensive application or a memory intensive application, so then the response time would vary depending on which platform you are using. So now you saw there is a heterogeneity exists at the hardware level, at the location level, and at the platform level. So now we can make a heterogeneous clusters out of these. So let's say with the hardware configuration based, so I could have a cluster with the not three lambda, but the three kinds of deployments. So one with a 256 MB, another with a 512 MB, and 1024 MB. So same function deployed with three different configurations. So depending on the requirement, I can then send it to any of these deployments. The other could be location based. So maybe the user is in the US East, so I send the request to the US East or to the Europe or to the edge location. So this becomes a location based heterogeneous clusters. Then the third one is the platform based. So I can run my same function on all different platforms. So like you can see AWS Lambda, Cloud Functions, or your own private cloud with OpenWhisk or OpenFast. So you can have the same function running over there, and depending on the requirements, you can send the request to any of these platforms. So now the question would come, why I need this,
Could you maybe give an example of why would you use cloud functions and not AWS?
Yeah, so I was coming actually. So this is the slide which is why I need these heterogeneous clusters. So one of the function is to use the specialized architecture. So for example, in GCF, so previously, I think it's around 2 months back, they increased the memory you can specify for a function to 16 GB. Previously, it was only 8 GB. And AWS Lambda has 10 GB. So if your application or a function requires, let's say, more than 10 GB, so you cannot use AWS Lambda. You have to use the GCF only over there. Previously, it was 8 GB. And another factor could be like if you have, let's say, GPUs on your on-premise clusters, and you want to run the function, let's say machine learning training or something else. So you cannot use any of these two, GCF or AWS. So you have to build on your own platform, on the private cloud, like with OpenWhisk or OpenFast, and provide it as a service. And that's why if you want to use a GPU or TPU based functions, so you have to have it on your on-premise cluster, not on the GCF or the AWS. The other factor is the overcoming the limitation, which is already part of it, and other is the cloud bursting. So maybe let's say you have an application or a function which is which should mostly run on the private cloud, but if there are more users, then you can cloud burst it to the public cloud providers. So therefore, that's where you would use, let's say, like this platform-based heterogeneity. Like you are sending most of the requests to the on-premise cluster, and once you have a more number of requests, like let's say like on the Black Friday or something else, then you cloud burst it to AWS Lambda or GCF. The last is the data locality, data privacy. So there might be certain functions within the application which should always run on the on-premise because of the data locality and data privacy issues. And that's where you want your on-premise serverless platform also along with the public cloud serverless platform, so that you can send those functions to those where my data or data privacy are protected. Does this answer your question? So yeah, so does anyone have any else questions? So because I'm now moving towards the actual implementation side. Yeah.
Could you maybe give a ballpark of like how these, I think on slide 8 you have like these diagrams with,
Oh, sorry.
yeah, with like the response times.
Mm-hmm.
Could you give a ballpark of like how that compares to just hosting it using like Docker containers or?
Okay. So this one you see actually over here. This is the. So the question is, how does these serverless platforms compare it with the natively hosted with the Docker container or on the virtual machine actually? So this OpenWhisk, which is on the self-hosted environment, it's based on the Docker-based actually. So I'm directly using the bare metal, so that's why you can see amount of the time as compared to the other one is much less. So it's because it's directly on the bare metal. But I don't have the actual slide where you can actually compare them together, but you can find it on the Google. There are many papers describing how different clusters or different platforms behave actually, like for the cold start, for the response time, and many other things. So then I'll move to the next part. So now you see this all heterogeneous cluster. So now what is my problem is, so let's say I have a deployment which is within 2 regions and it has multiple clusters. One is the serverless compute edge cluster, which is on your on-premise or somewhere else. And there are then public cloud cluster, let's say like AWS Lambda, then the Google Cloud Functions, and it could be your on-premise private cloud like LRZ I have over here. And similarly for another region, it might not have the public cloud like the on-premise cloud over there. So now if the user is sending the invocations, how should I distribute these invocations across these different clusters? So if I send the invocations over here, so it might reduce the response time or it may increase the response time. So the question is how I can send the invocations from the users across these heterogeneous compute clusters distributed across edge and the cloud. So this is what the FDN is all about, the function delivery network. So as you can see the name, it's function delivery and then the network. So the network is the network of all these different compute clusters across edge and the cloud. And the function delivery is sending the function to one of these clusters and then sending the function invocations across those clusters. To give you from a very high level, so what this FDN is about. So you have public cloud clusters like AWS Lambda, Google Cloud Functions. Then you can have a private cloud with some certain compute platform, serverless compute platform like OpenWhisk. Then you could also deploy a compute platform, serverless compute platform on the HPC nodes, FPGA devices, edge devices, and then distribute the invocations across these heterogeneous clusters depending on the requirements. So let's say because I have a machine learning inference and it's better suited for certain FPGA devices than sending it to the cloud over here. And maybe the user is closer to the edge cluster, so I can send it to the edge cluster as compared to the cloud. So yeah. So currently in the version which I have currently, we don't support these two yet. The work is going on in the research. So it's currently we have all these others are supported. So this all makes the function delivery network. So now the question would be, so as you saw from a very high level, so there would be how we can create these multiple clusters. That would be the first question. So you saw AWS Lambda, Google Cloud Functions, or your on-premise clusters. So all are these very heterogeneous in nature. So how can I create them? The second would be, how can I manage them? So once I've created these clusters, the second question would be, how can I manage them from centrally, some software or something? The third question would be, how can I monitor these clusters? I require this monitoring so that I can make the decision of distributing the functions across these clusters, like based on the response time or the latency or the data requirements. The next would be, once I have this data, monitoring data, then how can I schedule the functions across these clusters which are distributed across edge and the cloud? Does anyone have any questions before I go more into the details? No? So I'll start with the first one. So the first one is how I can create these multiple serverless compute clusters. So how many of you use Terraform? One, two, very few. So Terraform is like a infrastructure as a code. So whatever you require, like a virtual machine or a S3 bucket or different types of instances, you specify that as a code within the Terraform. So within Terraform, you can write the HCL files, which are the HashiCorp files. And you are over here a developer or whichever, then you write these files in the HCL files. Then you can plan. So plan is like what all resources are required by those mentioned within these files. And then you can apply. And then those apply would go to any of these cloud providers like AWS or Kubernetes or anything else. So it's like writing your infrastructure. So like creating a virtual machine within the code. So once you click the apply, so it will automatically create the virtual machine. To give you an example, I have an example of creating an instance on AWS Cloud. First, you have to specify, let's say, like a provider. So provider, I'm using AWS, and in a region US East 2. Then the next thing, as you remember, either on AWS or GCF, you were specifying certain firewall rules, like which ports to be open. So here you have to create a security group where you can specify which ports I have to open and from where the inwards network can come from, like here from all IP addresses. So once you have this, then you can specify the AWS instance, so which I call it as a my instance over here, and then the AMI, which is the Amazon machine image, so which virtual machine image I want within my instance. Then the type of the instance, security group, which I specify over here, and some user data. So this user data is like a startup script. So if you specify within the AWS, you can specify certain startup script and the tags information. So this is all you require for creating a virtual machine instance from the Terraform. So after this you have created it, then you can just specify Terraform apply, then it will be created on the AWS cloud for you. So this is one part. The other is the Ansible. So anyone have used Ansible over here? Yeah, 1, 2, 3, few of them. So Ansible also is quite popular these days because, so let's say you have a virtual machine now and you want to install the packages. So you have to SSH into the virtual machine and install it manually. But if you have to repeat this process again and again for thousands of virtual machines, it would be like it will take a lot of time. And it can be possible that while you are doing this manually, there can be certain errors. You skip some commands or you do something else. So that's why the Ansible is there. So Ansible is like an IT automation engine to automate the cloud provisioning, installation of certain parameters, certain packages, configuration management, application deployment, and other requirements, whichever you want within the virtual machine. To give you an example, so over here you can see what I'm doing over here, uninstalling the old packages. So like Docker engine, docker.io. So I'm uninstalling them and installing certain packages. So what Ansible would do is it will take the virtual machine IP address, automatically SSH into that, and run through all of this specification which you have written as part of the Ansible notebook. So in Ansible, this where you write this thing, this is called as a playbook. So I'll show you what this playbook is about. So now, so the question was, how can I create these multiple clusters? So what I use is Terraform. So Terraform creates the nodes, master node and the worker nodes on a certain cloud provider like LRZ cloud. And this master and the worker nodes are required for starting a Kubernetes cluster. And Kubernetes cluster is required for running a open source serverless platform like OpenWhisk or OpenFast or Knative. So all of these platforms require Kubernetes cluster to be set up. So Terraform is just creating the nodes and specifying them into an inventory file. So this inventory file would have the host IP addresses, so like all these nodes IP address plus the username and the password or the key information, which will be taken by the Ansible. So Ansible now knows all the different host information. You can separate them into different inventory files depending on the roles. So like I want a master to run separate things on the master and on the worker nodes. So you can separate out in the inventory files over here. So what this Ansible would do, it will check the playbooks, and each playbook would be specific to a certain roles over here, like a master or a worker node. And within the playbook, you can have roles, which they call it as so that for installing the packages, installing the Kubernetes, deploying the serverless platform. So once you have all this, then the Ansible would SSH into master and the worker nodes and deploy or run all the package installation, Kubernetes installation, and everything. So in the end, I would have like some platform like OpenWhisk or OpenFast running for me. So that now it would be easy for me if I written this file once, so I can recreate this platform again and again on different cloud platforms. So in the end, so I have like on the left side, the Terraform and the Ansible creating these multiple clusters. So one thing to note over here that AWS Lambda and the Google Cloud Functions does not require the virtual machines to be created. So you just create the virtual machine or a data, like you just create the functions, and the data is created as part of the Terraform, not the function itself. Function is coming from a separate part within FDN. We will see about it. So for the other clusters like OpenWhisk and the OpenFast, which is the edge and the private cloud clusters, so we use the Terraform and the Ansible for creating them. So any questions? So before I go forward. So one thing which I forgot to mention is the edge cluster. So this edge cluster which we are running at our chair is from a different nodes. So all the worker nodes are the Jetson Nano devices, the NVIDIA Jetson Nano devices or a Raspberry Pi, and the master is a virtual machine. So master like some virtual machine, and all these different worker nodes are the edge devices. So this is we call it the edge cluster. Yeah, so this is how we create the clusters. So now I have the clusters. So the next question is how can I manage these clusters? So does every one of you remember the Kubernetes architecture? So within the Kubernetes architecture, there is a kubelet which runs on every worker node, and that kubelet is managing all the commands given by the master node to the worker node for creating the pods and everything. So while designing this, I thought, why not use that idea? And so there exists a project called as a virtual kubelet. So this was created by Microsoft around 2017, 16, somewhere around that. So what in the actual Kubernetes cluster you have is over here. So you have a kubelet running on every worker nodes, which are responsible for managing the pods on these nodes, worker nodes. So what virtual kubelet does is it gives the illusion to the master node that there exists a node, but there is no node. So it will give the illusion to the master node that there is a node, which if you want you can schedule on it, but there does not exist that node underneath. So it's like a virtual node. And for implementing the virtual kubelet, so virtual kubelet is there, but for let's say, so as part of this kubelet over here, the node over here, so one has to implement the APIs for managing creating the pod, updating the pod, get pod, and other functions over here. So that you can do on these worker nodes over here. But within the virtual kubelet, you don't have the actual node over there. So you have to map these APIs to something else so that this can be managed. And that something else in my FDN is the actual serverless compute clusters. So what happens is now for each compute clusters, I have a virtual node, and this virtual node is part of the management cluster or FDN management cluster. So representing each of the compute platform underneath. So now what happens if I run an application or a pod or a function from this FDN management cluster over here and want to schedule on this thing, let's say this is pointing towards the open fast cluster. So then this particular virtual node should have the APIs for translating the pod scheduled on this to the function on this thing over here. So similarly for OpenVis, Cloud Functions, and AWS Lambda. To give you an idea, so here is an example. So let's say the function which I showed you initially, it's called as the gzip compression function, and it is at a certain Docker repository over here you can specify. And then there are certain environment variables. So these environment variables specify, let's say, like the function memory required by the function, timeout, concurrency is the number of instances which the function can use, and then the virtual kubelet node where this function should run. So what the management cluster would do, it will translate this into the function required for those specific compute serverless compute platform. So now, so you can see the advantage of this. I just have to write this one YAML file, and then you can easily map it to any of these serverless compute platform. So before that, you have to write for each of the serverless compute platform some different configuration or run through different CLI parameters for deploying on them. So this is how it looks like if you see the Kubernetes dashboard. So like different virtual kubelets representing different nodes in the FDN management cluster. Yeah.
So would the create pod call, would it be like an invocation of the function or the creation?
So the question is the create pod command, which I have over here. So this is the pod. So once you do a create pod command, it will create the function, not the invoke it. So once the function is created, I know that it is on this thing. So FDN knows the URL and everything for which then it can invoke from there. Any question before I move towards the next part? So the next is, now we have the clusters. We can now manage those clusters. So next is how can we monitor these clusters? So by monitoring means I want to collect different data, different metrics from each of these clusters, like the CPU utilization, memory utilization, or the response time of each function invocation. And for that, we created a tool called as FDN Monitor. So it is like a sidecar attached to each virtual kubelet nodes. You can see over here. What it does, it pulls the different metrics from each of the platform. So like each platform has their own monitoring tool. Like if I'm deploying OpenFast, then it is deployed with Prometheus. If I'm using AWS Lambda, it is using CloudWatch. So this platform, this tool will pull these metrics from here and aggregates them into a database, which can then be visualized to Grafana or can be used by the FDN for other analysis. The problem you can see over here is that each platform has a different representation of different metrics. So like AWS Lambda would have a different name, OpenFast would have a different name. So this is the responsibility of this FDN monitor to put them into a common name, standard name, which can then be used by the Grafana or FDN for later analysis. So I'll skip this slide. This is just a sequence diagram where you specify the configuration, and this configuration comes through the virtual kubelet, and then all the metrics required by FDN, it keeps on looping and collects it from the serverless platform monitoring tool, aggregate them, save them into the InfluxDB or the monitoring database, and keeps doing this process again and again. So just to give you the like a high level view, so what all metrics we collect. So this is the metrics from the K8s Kubernetes, which platforms are based on the Kubernetes. So you can see like the pods, CPU sum, the nodes, average CPU usage, the memory usage, the disk write. I think the interesting one is the AWS. So we have the AWS collector, which collects the information for invocations, how many invocations have happened to the AWS Lambda. Concurrency, as I mentioned earlier, concurrency is the number of function instances running, the execution time, the data from logs, or the more important is the memory utilization. So as part of the AWS Lambda and the Google Cloud Functions, you can see we cannot collect the infrastructure metrics like the CPU usage or the virtual machine or the container because it is hidden from the user. So we can only do that on the on-premise cluster or the edge clusters, which are where we have the full more access as compared to the AWS Lambda or the Google Cloud Functions. So this is how the table looks like. So like if you see AWS Lambda, GCF, OpenFast, and OpenWhisk, so there are different categories: platform-centric, very specific to the platform-centric, and the function resource usage, so how much functions are taking within that platform, then the infrastructure-centric. So this part is only, you can see for the OpenFast and the OpenWhisk, because this is your self-hosted environment. You don't have for the AWS Lambda and GCF. And also for the function resource usage, from AWS Lambda and GCF, you can only get the memory use. You can see over here. And then the others are the invocations, the concurrency, duration, the memory allocated to the function. And this is what the FDN names it within the FDN monitor actually, like a standard name which I mentioned earlier. So just to give you an idea, so this is how it looks like within the Grafana dashboard. So like different clusters representing the CPU usage for each clusters. And this is the infrastructure usage dashboard. So it will be only for the open source platforms. Then you can see the CPU usage, memory, disk, read write, and the disk write bytes. Similarly for the function usage as well. So how many invocations have happened, the execution time, the 9% 90 execution time, the CPU, memory, and different results. So for each of the platform, depending on which metrics are available, so we will push them over here and showcase into the Grafana dashboard. Yeah, so that's about the monitoring. So how we collect the monitoring part. Any questions? So the next is the scheduling function. So this is the most complex part into the FDN, but I'll not go into the more details. I'll just give you a very high level picture. So on the right side, you have these different virtual kubelet node representing the actual compute clusters. And from there, you get the data in the InfluxDB, and it is taken by the FDN backend server, which is responsible for scheduling the function across these different clusters. So this is done using the modeling also. So there are different types of modeling which are done as part of the FDN. One is the performance modeling. So like if I run this function on this cluster, how much my response time would be. So all those kinds of a modeling resides within this function modeling, performance modeling over here. The next is the functions interactions modeling. So which is like if I have an application consisting of 10 functions. So if I am sending a request from A to B, B to C, so how are those functions interacting? So like after how much time the B is invoked, after how much time the C is invoked. So all those kinds of modeling are done within this function interaction modeling. And this is done using the temporal point processes. So if anyone wants to read more about it, so you can check these papers over here. And so this, I'm not going into the details of this modeling part because it's out of the scope of this presentation. So the important point is over here, the courier, which we call it as the load balancer. So which is sending the invocations across these different clusters over here. And it is based on the HA proxy, which is an open source load balancer or a reverse proxy. And it maps the function request to the individual cluster. And this mapping is done through different levels. So one level is the delivering the policies, which is selecting the clusters. Let's say I have 10 clusters. And out of those 10 clusters, I want to, by some policies, I want to select a subset of those clusters. So that's what this delivering is doing. So it is selecting those subset of clusters. And this subset of clusters can be selected based on the function awareness. So if I have 10 clusters, out of those 10 clusters, in which cluster my function is running. So this would know. So this would select those clusters where those functions are running. The second is the data awareness. So if a function requires a certain kind of a data, so I should know where this particular data is situated in which cluster. And that's where this subset of the cluster would be selected over here based on the data. And once you have this subset of clusters, the next would be doing a load balancing between those clusters. And this could be based on the latency aware. So like depending on how big or small the cluster is. So this would be doing the latency awareness. And the other one is the capacity awareness. So how much the particular cluster can handle in the terms of the capacity. To give you a very high level picture, so we'll start from the bottom part over here. So let's say you are the clients or who are invoking the functions. And this goes to the load balancer of the FDN. And from the FDN, we have multiple policies, as you saw, function aware or data aware. And based on these policies, there is a second level of the load balancer sitting over there. So once you have this load balancer, it will know that I have to select this subset of clusters. So then it will do the load balancing within those subset of clusters. And the weights for the load balancing are decided by the control plane, and it is done through the load balancing algorithms. Yeah. Any questions here? So just lastly, this subset delivery points over here for selecting a subset of clusters, and then the load balancing, so load balancing between those subset of clusters. So just to give you an example, so like if you want to schedule a function which require, let's say, a certain bucket of images. So let's say I have all my images within this bucket called as images within some of the clusters over here. So like you can see AWS Lambda, Google Cloud Function, OpenWhisk, and all of these has images buckets plus models bucket. This does not have the images bucket. It has the images bucket. So what the user has to specify a header parameter, like what is required by the function. So over here is like, this is a header parameter that the function requires the bucket with the name images. And then the FDN would know that where these images bucket is present on which clusters, and then it will schedule to those clusters only. Yeah, so this is just a graph showing how once you have selected those subset of clusters, so how does the latency awareness work? So over here you can see OpenWhisk, AWS Lambda, GCF, and then you can apply a round robin policy between them. So like if I have a subset of clusters of these three platforms, I can do a round robin. So if you see OpenWhisk is performing like 0.61 seconds, 0.9 for AWS Lambda, and 1.20 for GCF for the same function. And once you apply the round robin policy, it will send all the function invocation one by one to each of these clusters. So that's where you can see it's reduced a bit, but not that much. Then there is a weighted round robin where we manually put some weights for each cluster. It is still not that low. And then there are different algorithms within the FDN, which we call it as the auto-weighted round robin, and a per function auto-weighted round robin, where the weights for each clusters are automatically decided based on the function invocations. And you can see it's quite less. And this is, you can see how the weights are within each of the clusters changing over time. Yeah, so I have all my questions solved. So in the end, this is how the FDN looks like from a architecture point of view. So you have on the underneath the infrastructure clusters, different serverless compute clusters. Then on top of there is a monitoring layer which is attached to the virtual kubelets. And then on the right side you can see the main management part where the cluster management is there, the function management, the data orchestrator. So the data orchestrator is responsible for managing where my data, to which cluster it goes. And this is for the modeling, this is the control plane. And so from here you can see the request goes to the load balancer and to the individual functions. And there are different APIs for different kinds of a user, like a normal user, developer, admin, for configuring the whole FDN part. So this is one use case of the FDN which we are currently working on, which we call it as the Fedless, for running the federated learning. So like managing the different clients of federated learning using the FDN. So your clients can be different functions which could be deployed on the GCF, Azure, or AWS, or on-premise. And how we do it, I'm not going into the detail of that. So if you want, you can check this paper out. Yeah, so that's the end of this part, the function delivery network. So if you want, you can check out and read more papers if you are interested into it. Or if you have any questions, you can ask me. I think it's a lot of information. I can manage it, yeah. So the next part is so the exercise, today's exercise. So let's do that after 10 minutes. So is that fine? So for 10 minutes break, and then we'll start with the today's exercise.